changes. If you ended up getting the 10th edition, there's no problem with using the 10th edition. We can take a look at the changes that they made from the better contrast. I have a white cursor. Can't even see it. You see it?
No.
Oh, there it is. So there are two kind of big changes in this, and that is this chapter, Entropy and Gibbs Energy. This is typically covered in Chem 1B, but that was moved to Chapter 13. Chapter 13 in the 10th edition is Solutions. And so if you look on the syllabus, there's a jump. We go from Chapter 12 to 14 in the 11th edition, because 13 will be covered in Chem 1B. But for the 10th edition, we're just going to go 12 to 13. And then they moved the chemical kinetics. This used to be Chapter 14, and then they moved it to Chapter 20. And so those were the two changes that they made. They moved the what we call thermodynamics part 2 to Chapter 13, and kinetics from 14 to 20. Other than that, it's the same book. And so you can read about the book, the organizational structure here. Like the previous editions, this edition begins with a brief overview of core concepts in Chapter 1. And then we introduce atomic theory, including the periodic table in Chapter 2. So we'll be starting that soon. The periodic table is an extraordinarily useful tool, and presenting it early allows us to use the periodic table in different ways throughout the early chapters of text. In Chapter 3, we talk about chemical compounds and their stoichiometry. Organic compounds are included in this presentation, so we'll be looking at some simple organic compounds. The early introduction of organic compounds allows us to use organic examples throughout the book, and so I like that too, because we do use a lot of organic solvents and compounds in general chemistry. Organic, you guys know the difference between like inorganic and organic chemistry? Like if you look at it, it's because of the way carbon bonds, not a lot of elements like to form bonds to itself, you know, and especially long chains of bonds. Carbon does, silicon does, and so you can form long chains of carbon atoms and branches, and it likes to form 4 bonds. And so if you look at the number of carbon-based compounds, it's huge. And it's always increasing because they're making new ones, so maybe millions. But if you look at the rest of the periodic table, the number of compounds is like 500,000 or something that have been cataloged for the entire, you know, all the other elements. So that's why they had to split it off, because there's just too many carbon-containing compounds, and therefore there's organic chemistry. But you know, it's chemistry, so it follows the same basic rules as other stuff. And then you can read more about the organization of this book. Okay, let's go back to what we were looking at earlier. And so one of the things I like to do is I'd like to look at all the homework problems. Even if I don't do them, you know, I'd like to read it and see how they did it, you know, all of them. And it doesn't take that much time, you know. Right now I'm taking a lot of time because I want to try to work through them. But I would have gone through these. These are more like your basic problems. And so go through these here. And then we jump kind of to the advanced problems since we have limited time. That's what I wanted to do. So we left off with problem 69 here. And so let's finish that particular problem. And let me write what I had up on the board. So I simplified the equation. There's two equations, 2 unknowns type of problem. And so let me write this. Let's see, we had the volume of the chlorine solution in liters. And this is equal to 18,000 gallons plus the volume of the chlorine solution in liters times, and then let me just write the numbers since the units work out. In fact, I'm not even going to write the units here because all the units are going to cancel out and leave us with liters if we did the dimensional analysis correctly. So this is going to be 3.785 times 1,000 times 100 divided by 1 million divided by 7 divided by 1.10 divided by 1,000. All right, so what we're solving is for, now we have one unknown. The one unknown would be the volume of the chlorine solution, so we can call that X if we want. And so I'm just going to call it X. X is equal to 18,000 plus X times that. So let's do 18,000 times all this. Actually, let me calculate what this is here. So that's going to be 3.785. 3.785 times 1,000 times 100. Actually, why am I using my phone? I have a calculator here. Okay, 3.785 times 1,000 times 100 divided by 1 million divided by 7 divided by 1.1 divided by 1,000. And so this term here, so this is going to be 18,000 plus X times 4.9156 times 10 to the minus 5. And so let's do this times 18,000 times 18,000. Okay, this is going to give me 0.88480519. Often in calculations, I don't round until the very end, so I'll carry extra digits to minimize rounding error. You know, you're only allowed one rounding step. So I try to avoid. Doesn't mean you have to carry this many digits. You know, depending on how many sig figs we're allowed, this is overkill here, but it's all right. Okay, then I'm going to combine the X terms. So I'm going to subtract this from both sides here. And so what is that going to be? That's going to be 1 minus 4.915 times 10 to the minus 5. And that's going to give me 0.99995x is equal to 0.88480519. And then just solve for x. So I'm going to invert this times 0.88480519. I get 0.88485 liters. All right, how many sig figs am I allowed in this problem? Yeah. Actually, if you look at the first, this is only 1 sig fig here. Do you think that's exact? You know, do you think these manufacturers who make chlorinating solution mix it up so it's exact? No. In fact, it's probably just going to be.
A little bit between 3 sig figs.
I'm sorry?
It's going to be 3 sig figs, right?
No, it's going to be 1 sig fig because of this.
Oh.
7%. I would classify this as 1 sig fig here, because if they're mixing it up, they don't want to spend too much time. So anywhere between 6.5% to about 7.4% is fine. Because that way they don't have to be so precise and accurate. And it's close enough. Whereas other things like this 1 ppm, how many sig figs do you think that is? That's probably infinite because they probably want the pool right at 1 ppm. And so, you know, not a little bit higher, a little bit lower. It's probably infinite. And so I would have treated this one here, 3.785, how many sig figs? 4. This 1,000 is going to be infinite because that was the conversion. This 100 is going to be infinite because that's part of the 7 here. The 7 is going to be 1 sig fig. A million should be infinite. 1.10 is 3 sig figs. This 1,000 is going to be infinite. And this 1, you know, there's the density of the pool water, which was 1.00, which is, but I didn't put it in here because I could have, if it made a difference in the sig figs, I would have put it in here, but since I'd be multiplying by 1.00 and dividing by 1, I'll leave it out. And so we're really only allowed 1 sig fig here, and so this comes out to 0.9 liters of chlorinating solution. And so this is how much I need to put in. Now 0.9 liters, how many gallons is that? Yeah, so, yeah, let's do it. 0.9 times, or divided by, yeah, divided by 3.785. Which comes out to 0.237 liters. So about 2.2 not liters, gallons. 0.2 of a gallon, you know, or 0.24 or whatever you want to do. Is that very much? No, if you add 0.2 of a gallon to 18,000 gallons, was there a significant change in the volume? No. There's pretty much an insignificant change in the volume. If that's the case, what, you know, alternatively I could have done is this. How do we know, though? You know, you don't really know. We take a guess. We take a guess that the chlorinating solution, you don't want to be carrying like 4 gallons of chlorinating solution from the pool store, right? Usually you just want to buy a small bottle of chlorinating solution and pour that in. And so we're going to take a guess. What we're going to do is when we take a guess, we just make an assumption. So we assume that the volume of the chlorinating solution is much, much smaller than the volume of the pool water. Therefore, when we have this, the volume of the pool water plus the volume of the chlorinating solution, these are our 2 unknowns, is going to be about equal to the volume of the pool water. And so if we make this assumption, then the problem simplifies to this. The volume of the chlorinating solution is just equal to 18,000 gallons of pool water. And then we go from gallons of pool water to liters of pool water, and then from liters of pool water to milliliters of pool water, and then from milliliters of pool water to grams of pool water, and then grams of pool water to grams of pure chlorine, using the ppm, and then grams of pure chlorine to grams of chlorinating solution, and then grams of chlorinating solution to milliliters of chlorinating solution, and then milliliters of chlorinating solution to liters of chlorinating solution. And so it's basically the whole dimensional analysis setup we had in equation 2. And so we just need to do equation 2 only that I had there. The equation 2 is my numbering system that I put up there earlier, but it's the same setup. In this case, we only have one unknown, what we're solving for here. And therefore, it simplifies the problem. Now, if we did this, how different would our answer be? So let's go ahead and set that up really quick and just do the calculation. So how different would the answer be? In other words, is that assumption a fairly good assumption? And so if we start off with 18,000 gallons of pool water, then we need to convert that to liters by 3.785 liters per gallon. That gives us our liters of pool water. And then going to milliliters, 1,000 milliliters per liter, That gives us milliliters of cool water. And then we use the density, 1.00 grams per milliliter. And this is only good for pool water. A chlorinating solution has a different density. And so we now have grams of cool water, and then we know we need 1 gram of pure chlorine for every 1 million grams of pool water. And so that takes us, the grams of pool water cancel, and that leaves us with grams of pure chlorine times the chlorinating solution. We know that we're going to have 7 grams of pure chlorine for every 100 grams of chlorinating solution. That was this percent of composition by mass. And so grams of pure chlorine cancel. That leaves us with grams of chlorinating solution. And we know the density of the chlorinating solution, 1.10 grams of chlorinating solution per milliliter of chlorinating solution. And then the grams of chlorinating solution cancel. That leaves us with milliliters of chlorinating solution. And we want liters. So a liter is 1,000 milliliters. And that gives us liters of chlorinating solution. So let's see how different our answer would have been had we done the simplifying assumption here. And so we'll take 18,000 times 3.785 times 1,000. I'll skip this one. Divided by a million. Times 100. Divided by 7. Divided by 1.1. Divided by 1,000. I guess I could have canceled out the thousands, but I didn't. All right, so I get 0.88480519. When we compare that, by making that assumption, our answer is incorrect, because really the pool is going to have a little bit greater volume. But how big is that error? Is that significant? The error, And so here we accounted for the additional volume change of the pool, which is very small. But when we look at it, did it really make a difference? We're only allowed 1 sig fig. Did it make any difference? No. Now, if we had to calculate it to a lot more sig figs, then it would have made a difference, and we probably should have done it, the 2 unknown way. Does that make sense? This is a tough problem.
Would it be wrong to assume the pool water doesn't change very much?
No.
So it'd be okay.
You're right. If you look at the solutions guide, that's what they did. They just assumed the pool water didn't change much. So I should have made a copy of the solutions guide to show you. Actually, this was what, 69? We actually, in Chem 1B, this is called the simplifying assumption. Yeah, if you look at their answer, they start out, they didn't even make an assumption. They just said 18,000 gallons, and ignored the extra, volume. So they didn't even, but in Chem 1B, we usually do this. We state our assumption outright. We're going to assume that this, and this is called the simplifying assumption. And it's very common. It's not so common in Chem 1A, but it's very common in Chem 1B, where we assume that the change is very small, and therefore we ignore the change. And that just makes the math easier rather than having 2 unknowns. And we have to have 2 unknowns and 2 equations. We just have 1 unknown. It makes your life a lot easier. Unfortunately, we can't always make that simplifying assumption. Sometimes it fails. That is, let's say we use a simplifying assumption, and then we find out, we're going to be adding 500 gallons of solution. If we're adding 500 gallons, that's a huge change. You can't do that assumption in that case. case. And so in Chem 1B, you learn about the justification for the simplifying assumption, what kind of percent change you have. But it's a little bit circular, the justification is based on making the assumption, but it's okay because it's close enough. All right, let's take a look at number 70, since we're going to look at all these problems. And some of these, they're kind of time consuming, so you just look at how they are solved. Oh, one thing we have to do, and you have to get in the habit of this, is show me the units. So this is liters, and then I'd like to see the rounding step. So I'd like you to carry extra digits and then show me how you rounded this. Since we're only allowed 1 sig fig, we round this to 0.9 meters. So dimensional analysis, this is like 90% of the problem, more than 90% of the problems you do is you just try to cancel out the units. Sometimes you come up with a little flow chart strategy here. I'm going to do these conversions, but normally I don't. I just go ahead and start trying to cancel things out. That's it. So number 70, a standard 1.00 kilogram mass. Do you know where the standard 1.0000 kilogram mass is?
Paris.
Actually, in Paris. Did I already ask you that? No, it's Paris. Yeah, last year I did ask you that. But it's not made out of steel. Do you know what it's made out of? Platinum palladium. It's platinum palladium alloy. It's very dense, so it's quite small. But if you have a steel one, steel's a lot less dense. The density of this steel is 7.70. There's grams per cubic centimeter. Is steel a substance? Is it pure? Is steel like a compound or no? Mm-hmm.
Steel is an alloy.
Yeah, steel's an alloy. Alloys are homogeneous mixtures. I mean, it's homogeneous. It's comprised mostly of iron and some other elements in there. Hopefully this is stainless steel because a lot of steels are prone to rust. They have lots of different grades of stainless steel. Some stainless steels can rust, 430, but there are other stainless steels that retain its luster. And so stainless, I'm guessing if this is a standard mass, when they use this word standard, what does that imply? Have you heard the word standard and standardized? What does that mean? Rather than a 1.00 kilogram mass is to be cut from a bar. They threw in standard in there. A standard is very common. We have primary standards. Have you ever heard of primary standards? In titrations, we do standards. Like we have a titration in Chem 4. Part 1, the Chem 4 titration is standardization of sodium hydroxide solution. And standardization is a process of determining its composition to as high of a degree of accuracy and precision as we can. And so if you have a standard, this standard is used for calibrating. So if we cut a 1 kilogram standard, then we can use that standard to make sure our balance is reading 1 kilogram. But this wouldn't be a primary standard. Primary standards have to be very stable. This would rust. If it rusts, the mass would increase because it's gaining oxygen. Or if it flakes off, the rust can break off and the mass would decrease. And so this is very weird to have a standard made out of steel, unless it's stainless. Stainless, okay. But anyway, it's because, so this is a somewhat convoluted problem. And some convoluted problems I don't really think too much about. I just think, let me just see how they solved it, because I think it's not maybe as practical. But we'll do this one nonetheless. So A standard of 1.00 kilogram mass is to be cut from a bar of steel. So 1.00 kilograms, that's extensive here, so it's fixed. So this is usually are given, you know. Sometimes our given is an intensive, you know, like a ratio. But most of the times our given is going to be an extensive, you know, some amount. It's going to be a bar that's triangular, like this. And so what we have to do is we have to figure out the how many inches long must this section of the bar. So we need the length in inches here, because we have a long bar which is more than that, and that's 2.5 inches on the side to 3 sig figs. The density is 7.70 grams per cubic centimeter. It's 7 times heavier than water, more than 7 times heavier. This is going to sink. So what is length? Well, what we want to know the volume, right? Because here, there are different ways we could do this. We could do this algebraically, or we could do this dimensional analysis. Right? So if we start off with our given, 1.000 kilograms of steel, then I need to get rid of kilograms, or kilograms of steel. Do I have anything with kilograms of steel? No, but I do have something with grams. This is grams of steel per cubic centimeter of steel. And so I'm going to just get rid of kilograms here. And we'll just go to grams. 1,000 grams per kilogram. It's exact. That's infinite sig figs. So I have 4 sig figs, infinite 4 sig figs so far. For standards, we want a lot of sig figs, you know, as many as possible. So we'd like to know the density of more than 3 sig figs, and we'd like to know this length of more than 3 sig figs, but it looks like we're going to be limited to 3 sig figs. So now we have grams of steel. Now we have something that can get rid of grams of steel. That is, we have 7.70 grams of steel per cubic centimeter of steel. All right, now we have different choices here. We can stop here and then make another equation, you know, because we want the volume. Cubic centimeters is a derived unit, and this is in inches here. So what we could do is we can convert our inches into centimeters, or we can convert our cubic centimeter into cubic inches. Which way do you want to go?
Cubic centimeters, inches.
Okay. Now, there are different ways. I could stop here. So if I stop here and then do algebraically, or I can continue doing dimensional analysis. I'm going to continue doing dimensional analysis here. Although stopping here might be easier to see this, but I want to show you something with this particular problem. And so now we need to get rid of cubic centimeters of steel, or cubic centimeters.
Cubic centimeters.
Yeah, we're going to get rid of cubic centimeters. Because otherwise we go in circles here. Now, I want to go from cubic centimeters to what?
Inches cubed.
Inches cubed. So I know there are 2.54 centimeters per inch. Does that work?
No.
No, that doesn't work. What do I have to do to fix it?
Cube 2.5.
I need to cube everything, 2.54. So it's 2.54 cubed, and then inches needs to be cubed here. And the 1 needs to be cubed. Everything needs to be cubed here. Should I cube the cube? No. Okay, now it works. Okay, then that's going to give me cubic inches. Now, there are different ways you can handle this. I'm going to do it this way. Do you know the volume of this is going to be the area times the length? The area times the length will give me the volume. And so I need to figure out what is the area of this triangle, and then just multiply by the length. What is the area of an equilateral triangle? Here.
It would be the length of both sides, which is 2.50 times 2 divided half.
Okay. So it would be, or the formula would be what? 1/2
1/2,
base times length?
yeah.
Okay. 1/2 base times length.
Let's see.
So the area here of this is 1/2 the base times length. So that's going to be 1/2 the 2.50 times, well, the height. Is it the height?
It's based on height.
Oh, is it based on
Yeah.
It's based on height, yes.
Yeah, what is the height of the equilateral? We have to do a little bit of.
Yeah, you have to do some.
What if you forget this stuff?
It's just, it's
Exactly.
You
root
could just look in the
3.
solutions manual.
Yeah, we could look at the solutions manual. But there's also one other place we can look.
Just it's 250 for A.
You know, Appendix A?
125 B.
Appendix A is mathematical operations.
Oh, nice.
And so if you forget some math, we can go here to Appendix A and maybe they have it here. Let's see what they have here. So they have exponential arithmetic. Okay, we don't need that, I think. But if you do, this is a good place to review. You know, if you forgot this stuff from Chem 4. This is keying in your calculator. It's good. Addition, subtraction, I don't think you need to review that. Multiplication should be all right. Division should be all right. Raising the exponential to power, extracting the root of an exponential number, logarithms. What else do they have here? Some useful relationship with logs, sig figs and logarithms, natural logs, algebraic operations. The quadratic equation. Then we have the method of successive approximations. Have you ever heard of that? The method of successive approximations is the guess and check method. Have you heard of the guess and check method? That's it.
Alright.
And so basically, if the equation becomes too difficult, we use the method of successive approximations to try to figure out the answer. So let's say I have 2x is equal to 6. So you start guessing, you know, I'm going to guess x is equal to 1. It's too low. Maybe guess x is equal to 5. That's too high. And then kind of narrow it down until we can get the right answer. And so this is the guess and check method. It's especially, well, you know, my calculator does cubics and quadratics. So I don't have to do that for this, but sometimes you have quartic, quintic, what's the next one, hexic?
Hexic, septic, octic.
Yeah, when you get these horrendous equations, it becomes very difficult. And so we do that when the math becomes too much. Quadratic I would just use, but if we have the fifth order, like this one, are you good at solving fifth order algebraic equations?
It takes a very long time.
It takes a very long time. Some people use graphs and all this other stuff. And so it would be useful to use guess and check. This is why you need to know some reasonable numbers to have as your initial guess. You know, what's a reasonable number for your first guess? Because it could be from, what, negative infinity to positive infinity? But some of those numbers just can't be. Well, they don't have a trig review, looks like. Uh-huh,
I have a ballpark answer for what the height could be.
okay. What is it?
2.165.
2.165?
Yes, or
Okay.
to three significant figures, that's 2.17.
Okay, well, we'll leave it at 2.165. This is a whole section on dimensional analysis. So this is useful to review. Chapter 1 doesn't really review dimensional analysis, it just assumes you already know it. you know. So if you want to go through a review of dimensional analysis, go to Appendix A, and they do. Like this is a 1, 2, 3, 4, 5, 6-step conversion here. Okay, there's no trig. There's velocity and acceleration, some physics, you know. Force and work, these are Newton's laws. You haven't covered those before. Force is equal to ma, very famous equation. Force is equal to mg. Energy is equal to mgh. And so sometimes we'll need some physics in this class. And so there's a little physics review. Magnetism, static electricity. Do you know what this law is called here? Equation B13. Very famous. We use this as like a first approximation, and we kind of simplify it. But do you know what this law is? When I was talking about, you know, what makes an alpha particle so reactive, it's because of its charge and its concentration, but charge and the concentration is going to be related to its size. That is, when we think about things in those terms, I'm using Coulomb's law. This is Coulomb's law. Coulomb's law is the force is proportional to the charge, Q1 and Q2. This is a charge on body 1, charge on body 2, and the distance between the centers. The distance between the center of charges is going to be related to the size. So it's kind of the size to the minus 2 power, or divided by the size to the square. So that's Coulomb's law. Coulomb's law is talked about in the Chem 4 book, but they don't give the full equation. So some physics here. Electricity is more for Chem 1B when we talk about batteries, that kind of stuff. Watt, what is a watt? Power. Electromagnetism. SI units, if you're ever curious what the SI units are, they're here. They're also in chapter 1, I think, as well. SI prefixes, a more complete table here. Derived SI units like volume, you know, cubic meters, area, square. Velocity, acceleration, density, molar mass, molar volume, etc. The SI unit for molar mass is weird, kilograms per mole. You know, we don't use SI units for everything. It's a lot of them just impractical. Then we have things like frequency in hertz, force in newtons, pressure in pascals, energy in joules, power in watts, charge in coulombs, electric potential in volts. These are the units here, though, in SI. So these are very important. Probably the one that you need to know the most is a joule. A joule is defined as 1 kilogram per meter squared. Kilogram meter squared per second squared is a joule. Sometimes we have to, instead of using J, capital J, we use this kilogram meter squared per second squared in its place. Units to be discouraged or abandoned. What units don't they like? Angstrom they don't like. And you know why people don't like angstrom? You know what's replacing the angstrom?
What?
The picometer. The picometer is replacing the angstrom. So let's say the diameter of the atom were 2.45 angstroms. You know why they don't like it? They don't like it because the decimal point takes up one extra character. If you needed one extra character here, then versus this, this would be 245 picometers. And no, if we express it in picometers, there's no decimal point there. It's just 245 picometers. And so they get rid of that decimal point. And so this is why they want to abandon the angstrom. But, you know, the angstrom's still used. It hasn't been abandoned. There are people who don't want to abandon the angstrom. The dying, the erg, the calorie, the atmosphere. You know, the calorie and the atmosphere, these two are going to be hard to abandon. The millimeter of mercury, that's going to be hard to abandon too, and the torr. Those are going to be hard to abandon.
They just want to keep bar.
What's that? Everybody wants to switch to bar and millibar, you know, because millibar is about the same as a millimeter of mercury, and a bar is about the same as an atmosphere. So. The problem is what is atmospheric pressure? The atmospheric pressure is 1.01325 bar, and so that's harder to remember than atmospheric pressure is 1 atmosphere. Yeah.
I feel the weight of my atmosphere.
So I prefer atmospheres, but we're going to have to be adept with both. And then we have these data tables. If you want the electron configurations for the elements, they're here for all the elements.
Oh, it only goes to 106. Yeah.
And then we're going to be using this Appendix D a lot. Appendix D for data tables. So, some stuff in the book. Unfortunately, the book does not have the area of an equilateral triangle, or not the, I guess we don't need it, or the length of the, or the height of the bisect there. So how did you calculate, how did you estimate it at one point?
I used 2.50 inches for each side.
Mm-hmm.
So with each side, that means that if we were to put it into a right triangle, since it is equilateral, you can say that C is 2.50 inches, and A plus B would be, well, I did B as mine, is 1.25 or half, because we are splitting the triangle right down the middle,
Okay.
right? And then we just figure out.
Solve for this.
Yeah. Oh, solve for A down the middle.
Okay. This one?
Yep.
Okay.
Which would be 2.50, was it 2.50 squared minus 1.25 squared. And then you would,
How did you solve for that?
Square root over.
And then take the square root of that?
yeah, and then just take the square root of it.
Okay. And then you got 1.675 or something?
2.165.
Yeah, 2.165.
2.165. 2.165. Okay, thanks. All right, so what did we get for the area then for this?
2.706.
Okay. So the area of this is 2.706. Square inches?
Yeah, inches square.
It's squared.
Is it
Okay,
inches?
and then we don't know what the length is in inches.
That's what we're looking for.
That's what we're looking for. So they'll put a little question mark here for the length. And so this is what we'll do here. So we have how many cubic inches of steel we need. And then we are going to figure this out from this here, that is, how should we do this? Have you ever heard of a composite unit? Okay, this unit is going to be a little weird. This is going to be 2.706 square inches times, I'm going to call it X inches here for the length, times X inches. And so this is going to give us cubic inches. Once I know what X is, then I can multiply it together, correct?
Yes.
Yeah. And that'll cancel out the,
Just get the 1 over the top.
I'm sorry?
A 1 on top of,
Yeah, okay. Huh. Will this give it to me? What am I
It
gonna set
does.
this equal to?
Yeah.
but it's no longer really like a conversion factor.
Yeah, it's not really a conversion factor. So probably what we should probably do here is this. We should probably do a combination of dimensional analysis and algebra. And so what I'm going to do here is, this is kind of getting convoluted here. So what I'm going to do is I'm going to not stop here. I'm going to stop here and calculate how many cubic inches I have. Okay, so let's go ahead and calculate the number of cubic inches. This will be 1,000 divided by 7.7 divided by 2.54 cubed. And so I got the volume of 7.9252 cubic inches of steel. Is that what you guys get? All right, now this volume has to be equal to this, so that's going to equal the area, which is going to be 2.706 square inches, times the length, which is going to be x inches. Area times the length. And then just solve for the length. And so I'll take my 7.9252 divided by 2.706, and that gives me 2.9287. And so the length, or x, is equal to 2.9287 inches. Okay, how many sig figs am I allowed? 3. So we'll just call it 2.93 inches. Okay, if you have the solutions guide, you just check your answer. Normally you double check it. If it were a test, you got to double check it yourself. But if you have the solutions guide, we'll just check the answer and see. That way, but the solutions guide isn't always right. I said there are a couple of errors in here. And so they got the length of 2.93 inches. So we're good. Okay. Uh-huh.
How do they do it in the solutions?
How do they do it in the solutions manual?
Same thing.
Let's see. Okay. This is what they did in the solutions manual. They stopped here. So they went and they got cubic centimeters of steel. Okay. And then they got the area in square inches. So they got 2.706 square inches. Same here. And then they set up an algebraic equation. The algebraic equation they set up is this. They said the length is equal to the volume divided by the area. And then they plugged in the numbers here. But the numbers didn't match. So let me show you what they wrote here, just so you can see. I mean, there are lots of ways you can solve this. And so they put here for the volume, they put in 129.87 cubic centimeters of steel. And then they divided by the area, 2.706 square inches. And then they converted the centimeters into inches. But they did this. They converted the area here. And so what they did was they put 1 inch here, 2.54 centimeters here, and then squared this. So that's going to cancel out the square inches. Normally, in dimensional analysis, I cancel the numerator. So if you look here, it's cubic centimeter, but here it's square centimeter, so it doesn't quite cancel. But it leaves us with centimeters. And then if that leaves us with centimeters on the top, so the inches cancel, and the centimeters cancel here, and that leaves me with just centimeters to the power of 1, then they just convert that to inches. So they went 1 inch here and 2.54 centimeters here. And then the final centimeters cancel, and that leaves us with inches, and they got 2.93 inches. One thing I don't like about the book is they don't show me how they rounded it. I want to see this number before rounding, and they never show it in the solutions manual. Maybe to save space. But I'd like to see you rounded it from 2.928 to 2.93. 71, the volume of seawater on Earth is about 330 million cubic miles. If seawater is 3.5% sodium chloride by mass and has a density of 1.03 grams per milliliter, what is the approximate mass of sodium chloride in tons dissolved in the seawater on Earth? 1 ton is equivalent to 2,000 pounds. That's by definition, so that's exact. So this looks like just a straight dimensional analysis problem. You know, there's probably a lot of steps. That's probably why it's advanced. So what am I going to start off with as my given? Well, usually the given you want to start off with an extensive quantity, like an amount. Well, what would we start here with?
Start with the volume of seawater.
Yeah, that's fixed there. So we're going to start off with 330 million cubic miles of seawater. Okay, it's very important that, when I say units, this is a composite unit here. It's not just cubic miles, it's cubic miles of something. And it's going to be seawater. We have to label that. For any advanced problem, you're going to have to do that. Okay, then we have 3.5% sodium chloride by mass. So how should I write that as a fraction?
3.5 grams of NaCl.
3.5 grams of pure NaCl per 100 grams of seawater, or NaCl solution. Seawater. And so if you take 100 grams of seawater, there's going to be 3.5 grams of sodium chloride contained in it. It's going to be pretty salty. Okay, the density, so how should I write this? It's not enough to write it. 1.03 grams per milliliter is not enough in Chem 1A. Maybe in Chem 4 that's enough because you just have 1 or 2 steps. In Chem 1A we have multiple densities, multiple steps, so how should I write this? I shouldn't write it as 103 grams. There are different ways I write this. So for example, if I did this, 103 grams per milliliter of seawater, like this, then I know this only applies to seawater. Or I write it like this, 1.03 grams of seawater per milliliter of seawater. So I can keep track of everything. And then I have 1 ton. 1 ton is equivalent to 2,000 pounds. This is exact. Got infinite sig figs there. It looks like I have 2 sig figs in this particular problem. Okay, so what are they asking for? They're asking for how many tons of sodium chloride is dissolved in the seawater in Earth. Okay, so what I need to do is I need to get rid of cubic miles or cubic miles of seawater. Well, we don't have anything that has cubic miles of seawater. And so I'm just going to try to get rid of cubic miles. And where can I go from cubic? I don't have anything with cubic miles, but I do have something with miles. Do you know miles to feet? Yeah. 5280 is it? 5280 feet per mile. But that's feet per linear mile, it's not cubic mile. So what do I need to do for this one? Cube everything, yeah. So this is gonna be 5280 cubed, feet cubed, 1 cubed, miles cubed, and then it works. How many sig figs is this? Infinite. This is happens to be exact by definition. It's 5,280 feet. I don't know why they picked an odd number like that, but that's exact. Okay, so now I have cubic feet. Where can I go next?
Cubic inches.
Yeah, I can go from feet to inches. That's pretty. So 12 inches per foot. But this is linear, and so what do I need to do?
Cubic.
Cube. So it's 12 cubed, inches cubed, 1 cube, foot cubed. Cube everything inside. Okay, so cubic miles cancels, cubic feet cancels. Now I have cubic inches of seawater. Where can I go from here?
Centimeters.
Yeah, centimeters. Let's go there. And so 2.54 centimeters per inch. And then we'll cube the whole thing. And so we go from cubic inches to cubic centimeters. And then where can we go from cubic centimeters?
Milliliters.
Milliliters, yeah. We know that cubic centimeter is defined as 1 milliliter. And so 1 milliliter, 1 cubic centimeter. Do I need to cube everything? Here. Cube? No. This is by definition. It is. It's already a volume. And so if you take a volume and cube that, then it doesn't make sense. And so now we have milliliters of seawater. Well, here we have milliliters of seawater here. So we can get rid of milliliters of seawater. That is, there's 1.03 grams of seawater per 1 milliliter of seawater. Okay, so now we get rid of milliliters and seawater. Okay, so now we have grams of seawater. So we either get rid of grams or grams of seawater. Do we have something that gets rid of grams of seawater? Yeah, we could use this, but this would just bring us in a circle. And so we would use the other one here. And so we have 3.5 grams of sodium chloride, pure sodium chloride, per 100 grams of seawater. So now we have grams of pure sodium chloride. And where can we go from there?
Pounds.
Pounds, yeah. Let's go to pounds. Okay, we probably want to use the, we could get by with a 3 sig fig, but you probably should learn the 4 sig fig. Do you know the gram to pound conversion for 4 sig figs?
435.6.
435.6? 453.6? 453.6 is correct. So we have 453.6 grams in 1 pound. And so now we're going to have pounds of sodium chloride. And then, well, if we have pounds, then we can go to tons. So it's 1 ton per 2,000 pounds. And now we have tons of sodium chloride. So we're done. Here, let's go ahead and calculate it. So that's going to be 330 million times 5280 cubed times 12 cubed times 2.54 cubed. Oops, I made a mistake. You hear that? 280 cubed. I have to hit an equals. Times 12 cubed equals times 2.54 cubed equals times 1.03 times 3.5 divided by 100 divided by 453.6 divided by 2,000. I 1.1252 times 10 to the minus 3 tons. Do you think that's correct?
No.
No, that's this is a ridiculous answer because it's way too big or way too small. Yeah, this is way too small. I made a mistake. Here, I'd have to rekey it. Did you guys get it? What did you guys get?
1.1 times 10 to the 17th.
Okay, give me before 1.1.
1.0931.
1.0931 times 10 to the 17th.
That's how I think it was gonna happen.
That seems more reasonable, doesn't it? What did you get, Tristan?
5.4659. 5.4659 times 10 to the 16.
Anybody else?
I got
I got
one
that.
point 38834 times 10 to the 17.
Any others?
Still working on it.
Still working on it?
I ran out of space at the last conversion.
I'd redo mine. Probably my calculation, but let me tell you what the book got. To the book, yeah. The book got 5.5 times 10 to the 16 tons. 5.5 times 10 to the 16 tons. So let's see, let's do the calculation again in the calculator and see what we get. So I'll try it again. 330,
He got 5.465.
330 million times 5280 cubed.
So many times.
Oh, I see. Times 12 cubed times 2.54 cubed times 1.03 times 3.5 divided by 100 divided by 453.6 divided by 2,000. Okay, now I got it. 5.4659 times 10 to the 16. Did you guys get the same? Okay.
I'm not getting it. I'm looking through mine.
Oh yeah, all right. So I just miskeyed it, I think.
I think I'll get it eventually. It's a calculator.
72. The diameter of metal wire is often referred to by its American wire gauge, AWG number. A 16 gauge wire has a diameter of 0.05082 inches. What length of wire in meters is found in a 1.00 pound spool of 16 gauge copper wire? The density of copper is 8.92 grams per cubic centimeter. Does this problem look familiar or sound familiar? This problem is quite similar to the bar, isn't it? And so we're starting to have some repetition in the problems here. And so this one's going to be very similar to the bar, except we don't have to calculate the area. Well, we do have to calculate the area. They're giving us the diameter, but it's at least a circle. So if it's a circle, then we know the area is equal. The area of a circle is equal to what? Pi r squared. Which I think they cover in algebra. So, so this is 16 gauge wire. It's weird, you know. Is 20 gauge thicker, fatter wire, or thinner? Thinner. It's weird. So the higher the gauge, the thinner the wire. And so 8 gauge is very thick. 16 gauge is pretty thin. A lot of applications use, like in houses, I think you use 12 gauge wire for houses. The thinner the wire, the hotter it gets. We got to make sure it can carry. Yeah. And so we know the diameter of this. The diameter is equal to 0.05082 inches. And so again, we're going to want the volume. And so the volume is going to be the area times the length. But here, the area of a circle is equal to, what's the formula for the area of the circle? Pi r squared. And so people remember this one, I think a little more than the others. And so pi, what should we use for pi? How many digits should we? You know, some people, I know this person who, on their phone, you know their passcode? They put in the first 50 digits of pi. The first 50 digits of pi or something. It's some ridiculous. Or was it the computer? I can't remember.
Wait, Professor, is
Yeah.
that true?
Some people know. Some people have it memorized. I don't know why, but they just want to have it memorized, and then they never forget, because if they forget it, they can just look it up, right? Or they pick an odd number like 49, so it's not so simple, or 51 or something. I
I
don't
know
know.
only a couple of digits.
I only know 3. Sometimes we need to know more, because this is how many sig figs?
4.
This is 4 sig figs, so I don't want to put 3 sig figs for pi here, because that's going to limit my answer unnecessarily, because somebody used a high precision, well, this is probably by definition, but somebody used a high precision tool to measure this. So if I'm just going to use 3.14, that's, you know what, a scientist, a practicing scientist would say that's lazy. You're lazy, you know, if you're going to do that. And so we're not going to do that. We're going to look for pi then. Unless somebody already has it memorized. Or somebody
And how many
I
digits
do
do we
know it.
want?
We want one more than the given.
So we
That
want
way we can minimize round off error. So if we have 4 here, I want pi to 5.
3.1459.
Wow, okay.
I want to look up, see if my memory helps.
3.14.
159.
159. Okay. Well, that's 6, so that's good. So we want it to 5. 6 is better. We get a little less rounding error. But 4, we get a little bit more rounding error. So we probably want it to there. And then the radius is just going to be that's 0.05082 divided by 2. I'm going to square that. And that's going to give us square inches. And so what is our area here? So I'll go 0.05082 divided by 2 equals square that times 3.14159. So this is how I'm going to keep track of sig figs. The way I keep track of sig figs is I'm allowed 4 in this calculation. So I'll go 2.028. But I'm not going to round it. I'm going to carry any extra digits as a subscript here. And I carry extra digits as a subscript to try to avoid rounding errors, you know, or minimize rounding errors here. So I'll carry 1 extra digit here. Sometimes I carry more, depending on how precise I need the answer. Okay, so we have the area, and the volume is just going to be the length times the the area times the length, or area times the height, or whatever. And so area times length. One length of wire in meters is found in a 1.00 pound spool of 16 gauge copper wire. So we want to know how long this wire is. And so what's our given? What are we going to start with here? The diameter or the pounds? Or the density?
The density.
Or the gauge?
Let's start with the density.
Start with the density?
The density.
It's best if it's possible to start with the extensive. Density is intensive. And so it's, what would be extensive? The diameter would be extensive, but we already did the diameter.
So it would be the
weight.
pounds.
The weight, the 1.00 pounds. That's not going to change. The number of grams and the cubic centimeters will change, you know. I mean, the ratio doesn't change, but we could have a lot more grams or we could have a lot more volume. And so we're going to start off with 1.00 pounds of what? Copper. And so we'll just say Cu for copper. Okay, then I'm going to try this dimensional analysis. So I'm going to go from pounds or pounds of copper. But I don't have anything with pounds of copper, so we'll just go with pounds. What are we gonna do? 1 pound is equivalent to 453.6 grams. This is the 4 sig figs. This is the 3 sig figs here, so I guess, all right. Okay, then what? Okay, so pounds cancel, that gives me grams of copper, and then where can I go from there?
You can use the density defined.
Yeah, let's just use the density here. That is 1 cubic centimeter of copper is equivalent to 8.92 grams of copper. And so the grams of copper cancel, and that gives me cubic centimeters of copper. Cubic centimeters of copper is the volume of copper here. I know the area, so the only thing I'm missing is the length. So I'm going to stop here and do it algebraically.
I think your area might be wrong.
The what?
The area might be wrong.
The area is wrong? Okay, let's, can you tell me what you got?
That's the same number plus negative. Times negative. 10 to the negative 3.
Times 10 to the negative 3?
So right back
Okay.
to decimals.
Then, yeah, I forgot. Sometimes I forget to write that in there. Okay, is that what you guys get? Okay, good. Yeah, that screws me up when I forget to write that. Sometimes you can immediately tell, the number looks weird. Sometimes it's hard to tell if it looks weird. So we'll probably stop here, except this is in, look at this, this is going to be in inches squared, and we have cubic centimeters here. So do you want to convert the inches into centimeters or the centimeters cubed into inches? Yeah, let's do the centimeters to inches. That way we can just add it here. And so we're going to have 2.54 centimeters for 1 inch up here, and then cube everything. 1 cube, inches cube, 2.54 cube, centimeters cube. Okay, now the units work out. So let's go ahead and calculate this here. And so that's going to be 453.6 divided by 8.92 divided by 2.54 cubed. And I get 3.1032 cubic inches. Is that what you guys get? Yeah? No?
Yes.
Yeah,
Okay.
I got it.
All right, and this is going to equal the area, which was 2.0284 times 10 to the minus 3 square inches, times the length, which we'll just call x inches. And then we'll solve for x inches, or x. I guess we'll just solve for x. So units are going to work out. Areas are square inches. So cubic inches divided by square inches is just going to give us inches. So I'll take that and divide it by 2.0284, 2.0824 times 10 to the minus 3. And I get 1.4902 times 10 to the third inches. And so that would be, how many sig figs are we allowed? 3. So I'll call 1.49 times 10 to the third inches, or 1,490 inches. Is that what you guys got? So we could just take a quick look, and is that what they got? Oh, they want meters, shoot.
Well, we have inches.
We have inches. Okay, and then we'll just convert this to meters. I have it still in my calculator, so I'm going to use this here and then convert it to meters. So how do I convert it into meters?
2.54 centimeters.
Yeah,
One
so
centimeter.
I'm going to go 2.54 centimeters per inch. Okay, and then what?
There's 100.
Yeah, 100 centimeters per meter. Okay, that inches cancel, centimeters cancel, that leaves us meters, so times 2.54 divided by 100. And I get 37.851 meters. 37.851 meters. We're allowed 3 sig figs, so I'm going to call this 37.9 meters of wire. Is that what you guys get? Let's see what the book gets. The book got... Oh, the book got something different. The book got 38.8 meters. 38.8 meters. So that's uh-huh.
It said 38.8, right?
Yeah.
That's why I got it.
You got it?
Yeah.
All right.
I also got it.
You got it?
I'm not sure of your error.
Yeah.
You switched early to inches.
Yeah, I don't know. All right, if you guys got it, then I'm estimated calculation error in punching it in to the calculator. Okay. I would check it. You know, it's easy to miskey things, so it's always good to double check your calculation on the calculator. If you have the answer key there, it should be fine. All right, let's look at number 74. The typical rate of deposit of dust fall from unpolluted air was reported as 10 tons per square mile per month. And so this is like a composite unit type thing where we have multiple units in here. So if I were to write this, I'd probably write this like this: 10 tons of dust per square mile, so right, miles squared per month. And so I'll just write MO for month. So in this I have tons of dust, I have square miles, and I have months. Express this dust fall in milligrams per square meter per hour. So in this case, this is, normally when we do dimensional analysis, we start off with an extensive property. In this case, we aren't. We're going to start off with an intensive property, because what we're going to do is we're just going to do a unit conversion here. And so they don't want it in tons. They want it in milligrams. So the first thing I'm going to do is I'm going to get rid of tons and go to milligrams. And so let's do that. And so 1 ton is equivalent to what? 1 US ton is equivalent to what? 2,000 pounds. 2,000 pounds in a US ton. So that gives me pounds of dust. And then I want to go to milligrams of dust. So I'll go from pounds to grams. That's 453.6 grams per pound. That gives me grams of dust. And then finally, 1,000 milligrams per gram. And that gives me milligrams of dust. Okay, so I have milligrams of dust on the top. That's what I want. And then they want it per square meter, not per square mile. So I need to go from square miles to square meters. And so I need to get rid of miles squared on the top. What gets rid of miles squared? The only one I know is miles to feet. And so what we're going to do is we're going to go 1 squared, miles squared, 5280 feet, and square both of those. And so that gets rid of square miles and gives us square feet. And then from feet I can go to inches, 12 inches per foot, and then I need to square everything. So 12 squared, inches squared, 1 squared, feet squared. And so, oops, this is upside down. Do you see that? Sorry. This is upside down because the feet don't cancel. So I need to put 1 squared, foot squared on the top, and then 12 squared, inches squared on the bottom. And now foot squared cancels. So I have square inches, and then from inches I'm going to go to centimeters. 2.54 squared centimeters squared per, oops, I'm doing it again. Doing it again because I'm canceling out the denominator, so I have that habit. And so I need to put 1 squared inches squared on the top, and then 2.54 squared centimeters squared on the bottom. And so the inches squared canceled, leaves me centimeters squared. And they wanted square meter. And so I know that I have 100 centimeters for every meter, and then just square everything. And so that gives me per meter squared on the bottom. That's good. And then the last one they want is, they don't want it in months, they want it in hours. And so we have to go from months to hours. And so let's just string on some more conversion factors here. So to get rid of months, where should I go from months to?
Months to days.
Or
Or
days.
weeks,
to
months to
days.
weeks
Months
would
to
be
days.
less. 1 month to 4
Months
weeks.
to week would be more easier, but
It would take longer, yes.
Well,
You
like
go from-
months to days and then days to hours.
All right, we're going to do months to days
It averaged 30.
because we go from week to days anyway. So
Yeah.
the average is what?
30
month is
days.
30 days? All right.
yes.
All right, so that gets rid of months. We have days. And then we're going to go from days to hours.
Yes.
Okay, 1 day is equivalent to 24 hours. And then from, oh, that's it, right?
Yeah,
it.
that's
All
it.
right. All right, so let's go ahead and punch this out and see if we get the correct answer. So that's going to be 10 times 2,000 times 453.6 times 1,000 divided by 5280 squared. Divided by 5280 squared. Divided by 12 squared. Divided by 2.54 squared. Times 100 squared. Divided by 30. Divided by 24. 3. And I get 4.8649, and the units here would be milligrams per square meter per hour. Is that what you guys got? Yeah? Okay. So we deposit about 5 milligrams of dust in a square meter per hour. Let's see what they got. How many sig figs are we allowed here? Um, 10 tons of dust. How many sig figs do you think that is?
1.
Probably 1 sig fig. You know, it's really too hard to be that precise. So our answer, we're just going to go with 1 sig fig. With 1 sig fig, it's going to be 5 milligrams per meter squared per hour. Okay, what did the book get? The book got 5 milligrams per meter squared per hour. All right, I guess we're out of time. We're gonna just, I'm only gonna do this for chapter 1 to look at all the advanced problems, but you know, it's something you can do at home as well. So we'll look at B, and then we're gonna continue with this. Tomorrow's gonna be another long lecture day. But we were supposed to have the quiz. I'm gonna push the quiz to tomorrow. I'll give you another day to memorize. You probably already have those memorized, right? No, you don't? Okay, then you have one more day to memorize.
Made a little note card last night.
I noticed you put the homework up, but there's